So, so far we did classical statistical mechanics, but now I think it is we know how to deal with classical systems, microcanonical, canonical, grand canonical. Now I think let's see how do things change when we deal with a quantum system. So therefore today in the rest of this lecture and the following lecture, what we will do is we will study quantum statistical. So let's see how we do it. Okay. So recall that in classical statistical mechanics, we started off with an isolated system n v e e plus delta. You know, a macro state is a macro state. The number of particles is 500 or 50,000, regardless of whether you treat it using classical mechanics or quantum mechanics. The number is going to be the same. The volume, this chalk, for example, it remains a chalk regardless of whether you want to analyze it using quantum mechanics or using classical mechanics. Okay, you may get incorrect answer in one case and incorrect answer and correct answer in the other case, but the chalk is a chalk. The chalk remains a chalk. Nothing happens to the chalk. Okay? So in the same way, what we do is that we start with an isolated system. The macro state is first as in the classical setting in B E plus delta. Again, n is of the order 10 to the 23. B is very much larger than the atomic volume. Everything remains the same. No change in these quantities. And we are dealing with short range interacting system. That is, if I write down the potential energy of the system, then we find that every particle is interacting with only those particles which are in its close neighborhood. It is not going to interact with all the other particles. It is interacting only with a few close neighbors. Okay, exponentially decaying interaction. So this description, whatever classical statistical mechanics, canonical, non-canonical, whatever we did there, or here, we assume that the system is short-range interacting. So I have a Hamiltonian, and the system is short-range interacting. Which implies that the energy is proportional to the number of particles. We use this extensively in all the lectures until now. Okay, so this is the macro state. What about the micro state? So recall that in classical statistical mechanics, the microstate will be given by just one minute. Just one minute. Yeah. So the microstate is given by giving the position, the values of the positions and the momenta of the particles making up the system. So in classical statistical, in classical mechanics, we had this to be the microstate, right? But so this was the situation in classical mechanics. But in quantum mechanics, you cannot give the values of the positions and the momenta simultaneously with same amount of accuracy simply because of the uncertainty principle. If you are able to tell the values of the momenta precisely, you cannot tell with same precision the values of the coordinates and vice versa. So instead of giving the values of the positions and the particles of the coordinates and the moment of the particles, you instead you instead specify what is the wave function of the system. That is to say that instead of giving the values of Pi's and Q's, you instead specify the wave vector of the system. How does it look like? Okay. And of course, if I tell you this macro state, then you are not going to get one single microstate. Why? Because I need to solve this equation to find the consistent microstates. So I need to solve this equation. Because any consistent microstate has to have energy lying between E and E plus delta, because that is the given macrostate. So therefore, how do I measure energy in quantum mechanics? I have to compute the expectation value of the Hamiltonian. So I sandwich the Hamiltonian between the wave vector. I need to solve this equation, and if I solve this equation, I'm not going to get one microstate, but many microstates. So what I do is that I label the microstates by key. So I'm going to get a set of microstates. And this set of microstates, these microstates are going to construct for me the ensemble relevant to the system. Okay. So this is the microstate. So for this given microstate will be this set. So this will be the set of microstates. And of course, each microstate will have its norm equal to unity, because each of the microstates is normalized. And secondly, I know how each of these microstates evolves as a function of time. So in the classical mechanics case, the microstates were evolving following the Hamilton equations of motion. In the quantum mechanics case, the time evolution will be given by the Schrodinger equation. So therefore, each of these microstates evolve in time according to the Schrodinger equation. Now what I can do is that I have this collection of microstates. Okay, there are many microstates. So just as in the classical mechanics, we talked about the phase space density. Namely, phase space density is a way to characterize the distribution of these microstates in the phase space. I want to see what is the corresponding quantity in quantum mechanics. Okay? Now, in quantum mechanics, one thing I cannot do, just because I cannot specify the momentum and the coordinate values with equal precision, I cannot construct a phase space the way I constructed it in classical mechanics. Classical mechanics, recall that we constructed the phase space by envisaging a situation in which I have a 6 dimensional space where each point represents a microstate and so on. So such a construction cannot be done here. Here I have to do things slightly differently. So let's see how I do it. The first thing that I do is that given this collection of microstates, what I can do is that I can define a quantity pk, which is the probability of getting the kth microstate in the ensemble. Remember that this one, these microstates, they comprise the they constitute the ensemble of the system. So in this ensemble, if I define pk to be the probability of getting the kth microstate in the ensemble. So what I do is that I have this whole long list of consistent microstates, and I ask how many of these microstates are psi kt. Okay, so the fraction of the total number of microstates which are psi kt is going to give me this number p. So this is a fraction. So when I sum over k, then I'm going to cover all possible microstates in the system. So therefore, this number should be equal to 1. Okay. Now, so therefore, I have this macrostate and many microstates, and I construct this ensemble. I define this quantity Pk, which is perfectly normalized to unity. Okay. Now, if you are in the microstate psi kt, and then if you have an observable O, so recall that in quantum mechanics, any observable, any physical observable is represented by a Hermitian operator. Right? A Hermitian operator has eigenvalues which are real and so on and so forth. So suppose O is an observable, a macroscopic observable. So I'm using the same notation that I had used for classical mechanics, classical statistical mechanics. This one is a Hermitian operator. Microstate, then what is the quantum expectation of O? This is simply given by psi kt O psi kt. This is the quantum expectation of macroscopic observable O. But then this is the quantum expectation provided you are in this kth microstate. But what is the probability that you are in kth microstate? That is pk. Okay? So therefore, I need to also average over that randomness. First of all, if I know for sure that I am in a particular microstate, then the expectation value is this. But I do not know for sure that I am in a particular microstate. I have only probabilities telling me what is the probability of being in this microstate and this one and this one and this one and this one and so on. So therefore, I need to do a further averaging. That is, this is the answer. Provided I am in the kth microstate, but the probability that I am in kth microstate is pk. So then I sum over all possible values of k. This is going to give me the average value of a macroscopic observable, where I need to average over quantum randomness. The quantum randomness is being averaged over in computing the quantum expectation, as well as the classical randomness or the classical uncertainty, simply because I do not know which particular microstate I am in. So therefore, I need to also average over that classical randomness and which is done here. Okay, this quantity. Now we will see that this one can be cast into a form that looks exactly like the classical phase space average. Okay, so let's see how one does that. We need to do it is to define something called the density operator of the system. So let's see how you define, how we define that quantity. Find an operator. So this is an operator, city operator. So you define it this way. This is summation over k, pk of psi kt. This of course is an operator because I am taking the bra and the ket in, in reverse order. That is, I first take the ket and then take the bra. Definitely rho is an operator. And it's a, yeah, it's very much an operator. So then what I can show now is that this quantity, which was summation over k, sorry, k psi k t, this quantity I will now show that is nothing but trace of rho with O. A trace is the future matrix trace operation. How do I show this? This is quite easy to do. Evaluate this guy, trace of rho times O. So trace means what? That I have to do this one, summation over L, let's say psi L for rho, I will use this one, summation over k pk of psi k t psi k t. This is my rho, this is my trace, and then there is a O here, and then this is psi L t. Now what I can do is that I can use the orthonormality. That is this psi k's and psi l's, they are orthonormal. So therefore when I do this, I get a Kronecker delta. So therefore I can do one of the sum. And then I will be left with what? I will be left with just psi k, pk of course will remain, psi k t o psi k t. Why? Because when I take the inner product, psi LT, psi KT, I will get delta of LK. So these two terms, this term and this term, when I take the inner product, I get delta LK. So therefore, when I do a summation over L, I have to retain only the term when L is equal to K. Okay. And when L is equal to K, this guy gets replaced by K. So therefore, I have this, which is nothing but so therefore, when I have to compute the average of a microscopic observable in quantum statistical mechanics, I have to do this operation, rho times rho. Derive a number of properties for this guy, but let me first mention how does it look exactly like the classical mechanical case. This rho, it has a name, is called the density operator. Let's see what we learned in classical StatMech. In classical StatMech, if you recall, the average of an observable was given by this quantity, O times rho of PQ dPdQ. And in quantum StatMech, I have a very similar expression. So I have O times rho, but then instead of doing an integral, now these are operators. So therefore, I multiply them and take that trace. Okay. So we see that the description in classical and quantum, they are very, very similar. Nothing much of a difference, arises as far as, doing the calculation and this thing is concerned. In one case, you have to do an integral. In the other case, you have to do a trace operation. Okay, so we can derive a number of interesting properties for this rho. So let me just do that. What we need to do is, of course, to ask how does rho change as a function of time. Why would it change? Because the cycles are evolving as a function of time. So let's see how does it change. So then I have to do this. A of del cycle T del T times cycle T. Plus it will be two terms. One term is this one, and the second term will be cycle T del cycle T del T. But I know how does this quantity be. I know that del cycle T del T and so which implies that minus I h bar sorry, did I do a mistake here? Therefore, if I take the conjugate of this one, I get this equation. H is Hermitian, so therefore nothing happens. So I just substitute it here. If I substitute it here, the first term will give me what pk times this guy is got it is h by I h bar psi k t psi k t. This is the first term. The second term will give me plus psi k t. Del del of this is psi k t h divided by minus I h bar. But pk summation over k pk of psi kt that is rho, and similarly here summation over k pk of psi kt that is also rho. So therefore if I combine these two and there is a minus sign, so what I get is 1 divided by I h bar of h commutator with rho, which I can write it as minus I by h bar of h. So this is the quantum equivalent of the classical Liouville equation. Recall that in classical mechanics, classical statistical mechanics, we have this formula that in classical technique, we have this formula del rho del t plus rho del rho del t is equal to minus of also bracket of rho with h. In quantum mechanics, you have to just replace quantum statistical mechanics. We have to just replace the Poisson bracket by the commutator. And what I get is del rho del t is I by h bar of rho h. So you see that things are very similar. Minus of 1 by I h bar. Then there's a minus sign everywhere, but the Poisson bracket gets replaced by commutator divided by I h bar. Then the rest of the journey is very, very similar. That so I have this equation del rho del t is equal to minus I by h bar of h comma rho. So, and for any macroscopic observable, I have this equation. This becomes a function of time because rho itself is a function of time. So then what does equilibrium means? It is again the same way as things are defined in classical statistical mechanics. So this guy, it becomes time independent. When you measure the value of a macroscopic observable, you find that the value that you measure is not changing with respect to time. So this guy becomes time independent. So this becoming time independent means that rho has to be time independent, which implies the rho thing becomes time independent. How can rho become time independent? Rho become can become time independent only if it uh, commutes with Hamiltonian. So it becomes time independent. I call it rho equilibrium. And what does rho equilibrium satisfy? Rho equilibrium satisfies this equation. Again, recall that in classical statistical mechanics, we had exactly the same conclusion. That when I am in equilibrium, then the phase space density also commutes with the Hamiltonian. In the same manner here, there is nothing called phase space density because there is nothing called phase space. But then I have the corresponding quantity called the density operator. In classical mechanics, the phase space density also commutes with the Hamiltonian. In quantum mechanics, the density operator commutes with the Hamiltonian. But the rest of it is exactly the same as it is done there. Okay. These things are exactly the same as it is in classical statistical mechanics. The ensembles are also defined in the same manner. So let me just do that. So the microcanonical ensemble will be rho equilibrium, the density operator that could be given by just 1 by gamma of MVE. And again, the entropy will be given by Kb log of gamma MVE. Canonical ensembles in microcanonical, the macro state is in the plus delta. In canonical, the macro state is NVT, and here the density operator again will have the same form that it had in classical statistical mechanics. So it would be just e to the power minus beta h. H is an operator, so this is an operator divided by the partition function z of NVT. But then the partition function is now defined in terms of trace. Fields of e to the power minus. Just as in classical statistical mechanics, you had to do an integral to compute the partition function. Here you have to do the trace. And again, the free energy, the N1 free energy is given by minus kBT log of z of NVT. What about the grand canonical ensemble? This also has the same definition that it had in classical statistical mechanics. These are the quantities defining the macro state of the system. And if I write down the phase space density, to be to the power beta mu n will be an operator minus beta h divided by q of mu vt, where this phase space density q of mu vt, what it would have exactly the same expression that we had in classical statement to the power beta mu n times the canonical partition function. So as far as the formalism is concerned, this is all that is there in quantum statistical mechanics. In US, everything can be carried forwarded, except in that whenever you have an integral, you have to replace it with a trace operation. And of course, operators have to be placed at appropriate locations, appropriate places, but that is it. Okay. So I think this is a good time to stop because I covered the whole of classical statement, the three ensembles, and I told you how to take them over these concepts over to quantum mechanics, quantum statistical mechanics, where we found that things are very similar, nothing new, excepting that you have to deal now with operators and matrix and trace operation, and that is it. Okay. So please tell me if there are questions. Big one.
Sir,
Yeah.
sir, the Liouville's theorem is also same proof or not? Dou rho by dou t is equal to minus Poisson bracket of rho comma h.
So the proof I gave you, no? So one was in classical statement. And today I proved the corresponding thing in quantum, no? Just a while ago. So the equation will be this. Let me just check the sign. Yeah. See, this one is exactly the same. I proved it today, no? Today I proved using the Schrodinger equation. You see, in proving this in classical static, I have to use Hamilton equations, but I cannot use Hamilton equations on the quantum side. I have to use Schrodinger equation, and that's what I did. I used the Schrodinger equation to derive this equation. I had used Hamilton equations to derive this one, but then they have the same structure. Okay?
Okay, sir.
Other questions?
Sir, how is the concept of this entropy defined in quantum mechanical, like statistical and concept of entropy?
Same way you find the number of consistent microstates, and then you take KB. Same definition, nothing, no change. You just count the number of microstates which are there in the system, take the log and multiply by KB, you get entropy. See, entropy, temperature, pressure, volume, number, they will have the same meaning as in classical statement. See, the method of computation could be different in classical and quantum, but a quantity is a quantity. It should not change when you go from one to the other.
Okay, sir.
Sir,
Yeah,
how about the quantum mechanical at low temperature?
low temperature.
And I mean, quantum systems behave at a low temperature. How about the quantum systems in low temperature?
No, high temperature, low temperature, whatever, you have a quantum mechanical system, the prescription is always the same. Why would it behave, why would it have a special behavior? I mean, as far as the framework is concerned, it is the same framework. In quantum statistical mechanics, the framework that I talked about today, the framework is the same. If you do the calculation, you may get a different answer at low temperature and high temperature. That's a different story. But the framework, we are now developing the formalism. The formalism, think of it this way. English is a language. The language doesn't change when you talk about statistical mechanics and when you when you recite a poem. Okay, it's the same English. But then the usage of words, how you place the words, that's different when you are reciting a poem and when you are doing statistical mechanics, or let's say physics or chemistry. So today we develop the grammar. Grammar meaning how to, what are the words that you have to use and the vocabulary and the grammar and so on. And the grammar, either you use quantum statistical mechanics or you use classical statistical mechanics. We talked about both the formalisms. So let's say there is a dictionary in English and there is a dictionary in Tamil, let's say. Okay. And now it's your choice whether you want to speak in English or you want to speak in Tamil. Okay. But then the question is, if you do that calculation for a particular system, the answer that you get may depend on, of course, I mean, whether you are at high temperature or low temperature, if it is a quantum system, classical system, that's it. We did not do any calculation yet.
Okay, sir.
What we do is that what we will do probably in the next class and the remaining 2 lectures is that we will consider a collection of non-interacting particles, but then particles that obey either Bose-Einstein or Fermi-Dirac statistics, and we will see that at low temperature you can make out the difference. That this is a fermionic system, this is a bosonic system by doing this calculation. We get an answer. The answer will be different for a system of fermions, will be different for a system of bosons. But when you raise the temperature, when you go to very high temperature, then you will find that both the fermionic system and the bosonic system, on doing this calculation, will yield the same answer. I hope you understand that this is the formalism, this is the framework. You apply to a particular system and you will get an answer. The framework cannot tell you what the answer will be up prior. You have to do the calculation. But these are the rules that we talked about, how to do the calculation. We haven't done the calculation. It's okay?
Okay, sir.
Any other question?
No more questions.
Okay, so then since there are no other questions, so let me just tell you quickly what we will do in the afternoon class is that we will consider a system of non-interacting particles. The plan of the afternoon lecture so that you can, so what we will do is we'll consider a system of non-interacting particles. Following either Fermi-Dirac or Bose-Einstein statistics. And then we will derive some important properties like for example, the number density and so on. And we will see that at low temperature for these two systems, you will get different answer. But when you go to high temperature, you get the same answer for both. And this is what we plan to do in the afternoon lecture. Okay. So maybe we can stop now and then reconvene at 1:30.
Okay, sir. Thank you, sir.